We talk about refraction, it's a lot more complicated because refraction takes place all over. So this is a glass plate, we can refract light through a prism like this. We can refract light through a lens, and here's a different kind of lens, and we're going to talk about all of these. So right now I have it set up. Again, my light source is right over here at the bottom of the screen, and we've got a glass plate that I'm going to draw. So the light is entering the glass plate here, and it exits on the other side over here. So again, I'm going to draw where it hits the glass plate, and I'm going to put a dot where the incident ray is going in. And I'm going to do the same thing on the other side where it comes out. So there's my refractive plate. I'm going to do the same thing. I'm going to draw the incident ray. It's the incident ray. And then I'm going to draw the refracted ray that leaves the prism, and it's going to be very interesting. We're going to call that RF so you don't get confused with reflection. Now, you'd think that this would be straight, but I want to show you. You can see here the ray must have bent when it went through the glass, because if it went straight it would have been up here. Instead it was down here. So I'll show you how it bent. So what you can see here is that the light entered the glass and it bent. And then when it left the glass, it bent again. And these two lines are parallel, but they're no longer, it's not lined up directly. See, if you look here, very clearly below, but it's parallel. So what happened? Refraction means that light either slowed down or sped up. And light basically travels the fastest in air. If you go into outer space, it's even faster. So it'll slow down in any other kind of medium. So this is called a medium. Glass is a medium, water is a medium, diamond is a medium. So what happened when the light came into the prism, which is glass, it slowed down, so it bent. That makes sense. Imagine running on a beach and you run straight into the water. You're going to slow down, and most of the time people fall. Okay? Then, when it left the glass, it sped up again. Okay? So, if we want to measure angles, just to prove that, we have to draw normals again. Call that a surface normal. We do the same thing for the refracted ray. The angle of incidence is a little I, and we measure that just to give you a measurement here. And that is 29 degrees. Okay, and I forgot to get an angle of 20 degrees. They call that little t, so you don't get confused with reflection. So little t, you can see, is smaller than the incident angle that went in, and that makes sense because it slows down. But watch this. If we do the same thing with the refracted ray, now the angle of incidence is inside, and it's 20 degrees. What do you know? It's the same. That would be, this is I2, we'll call it. That's 20 degrees. It's exact same in here, which makes sense, a parallelogram. And we find it is 29 degrees. That's T2, 29 degrees. So if you look, you have a 29 degree angle coming in. It slows down. 20 degree angle inside, and the other, now it's going out. It's a 20 degree angle going out, and it speeds up and bends away again. It's 29 degrees. An incident angle, okay, when it enters a more dense medium, air into glass, the refracted ray will bend towards the normal. When you leave the glass and go into air, air is less dense now than glass, it will speed up, meaning it will bend away from the normal. You can indicate the density of these tissues. All right, out here we'll call it N1, which is air. N1 is the index of refraction. And N2 is the index of refraction of glass, which is about 1.33. Air is about 1.0. So you can see this is much more dense. So N2 is greater than N1 as the light enters the glass from the air. Okay, so it bends toward the normal. Now, you can go in reverse. When it goes back into air, it bends away from the normal.